Good afternoon, everyone. I'm Shubham. So I'll start with my project, the PubMed Miner team. The basic goal of this project is that we at JCVI had a basic code base for PubMed Miner, and our goal was to identify the sequence features through the LLM prompt engineering. We had our goal that with the help of this code base, we will present this to our team members with some domain expertise and add their own use cases to the project. So we could develop our own project and get some more extraction accuracy with this. As I mentioned earlier, we are developing a AI-driven workflow system that automatically mines the latest PubMed papers and validate the viral sequences that it extracts and eliminate any possibility of false positives by improving the prompts and explore any strategies to use it for other use cases with other diseases. So the basic methodology that we followed earlier was with the help of the PubMed API, PMC full text, we were able to extract the full text of each paper that the user wanted. And with the help of some LLMs like Gemini, GPT-4 or Llama, you can use any one of them, even the LLMs that are provided by Argonne Lab, and cleaning the entire text into a structured mutation CSV and give a rule-based validation system to that and making it very user-friendly so anyone can just access this app with just giving the API keys into the sidebar. So in this hackathon, we came up the entire new workflow. The user will give the prompt or the papers that he or she wants to look at with a natural language text that will be converted to a PubMed query with the help of LLM. And you can also choose the PMID of the query that was given to PubMed. And then that paper full text will be given to the LLM with some prompt that we have curated for specific use cases. And we had to chunk these prompt and the full text because the token size was huge and we were using the free tier Gemini model or the other free tier models and giving that as a context to each LLM saying that this is the text and extract the mutation, the protein, the amino acids with the code that it mentions that mutation in this sentence and gave it in a structured JSON or CSV format. The new things that we added during this hackathon was we modified the prompt and also added the AI judge so that when we are extracting the mutations, it again verifies that the extracted mutations is accurately extracted and the AI is again judging the performance of the extracted CSV. This is the prompt that we try to integrate in the app where we are giving out the patterns to recognize for residues or amino acids or mutations. So we had to increase our accuracy. So yeah, this is a demo of how the app looks like. So you can query the PubMed query over here and select a date range. You'll get the list of PMID and the paper titles for which you want the mutation out of it. And this is the findings that the LLM will provide, the title name, the protein, the position of that mutation, the code that it mentioned over there, and the target type. So one of the enhancements that we did in the hackathon was we were able to minimize the rows or the columns where it was not giving out the exact mutation like A comma B was there. If either A was there or B was there, so we tried to incorporate both the mutations and some of the mutation were in the short forms. We had to make two different columns for that, a standard format and the short form format. And another enhancement that we did was integrating the natural language part to it. Like you can just type in, I want papers of influenza A or dengue, and it will just give out a PubMed query for that. And it will directly access the PubMed API for that. One new application or one new use case that we tried was with Alan. He used it for his bacterial virulence genes for Salmonella. And this is the PubMed search that we did with the modified LLM prompt. He wanted all the papers other than the review papers, and we integrated that change in that. And overall, the Results were good. The PubMed Miner app was flexible for his use case. So that was a success. And it was able to mine the scientific important mutations that he required. So these are the results. We were able to install and configure the PubMed Miner for all the team members and review the results of influenza A virus that we were working in JCVI, modified the prompts to include missing mutations. Rather than including only few mutation examples, we tried to incorporate all the mutation patterns in the prompt. We enhanced the PubMed keyword search using the natural language and accessing the AI to convert that natural language into a PubMed query. And we are still in progress to validate the results of the PubMed miner with the multi-agent system. Yeah, the future directions, as I said earlier, we will continue to configure a file that is useful for different use cases. Like for influenza A, this could be a prompt. For dengue, this could be a prompt. So everyone can use that kind of prompts for their own use cases. And we will still work on the AI agentic part to validate the results by asking the questions multiple times to make sure that we are getting a good accuracy of results. Yeah, continuing with HiPerRAG.
I'm going to talk about our HiPerRAG project. This is a high-performance retrieval augmented generation for scientific insights. This is a project we conducted at Argonne last year with the support of CEPI and BVBRC. Our motivation in conducting its research is the fact that in just biomedical domain alone, PubMed receives over 3 papers per minute today. And last year, they received roughly 1.7 million articles, whereas the average American scientist actually reads roughly 22 papers per month, according to a survey result that's pretty consistent since 2005. So as you can see, there's a massive gap between the rate at which information is being disseminated and being ingested. And LLMs, with their ability to process information at an incredible rate, are the candidate to streamline the process of ingesting information. So the onus of research is on the creation of new knowledge instead of processing incoming knowledge. So we built a RAG infrastructure that runs on an arbitrary high-performance computing system. In this case, we tested this on Polaris and Frontier and Sunspot, which was the predecessor of Aurora. And our pipeline starts with the scientific corpus. For this work, we had 3.6 million full-text papers in PDF form. Then, from those PDFs, we parsed the text. This is just text modality only. So going from the PDFs to text that can be fed into an LLM. And this resulted in roughly 16 million chunks that are self-contained, cogent flows of information, usually multi-paragraph information. Then from those chunks, we have generated questions. And the questions that were sampled from a chunk formed the positive pair, and questions that were not sampled from a chunk formed the negative pair, allowed us to fine-tune a purpose-built encoder that aligned the embeddings of questions with the embeddings of chunks that might be answering those questions, resulting in a system that shows superior ability to retrieve information from a corpus of over 3.6 million full-text papers. And our system actually scales pseudo-linearly to over 1,600 NVIDIA 100 GPUs. As a result, we were able to take a model like Mistral 7B and have it perform commensurate with the state of the art at the time of writing, which was GPT-4, speculated to have over 174 billion parameters. So we are really doing on par with a model that has an order of magnitude more parameters and trained on much more data than we have. So we are integrating this technology right now into the BVBRC chatbot. For that, we have roughly 450,000 full-text papers from the ASM journals. These are various journals in the field of microbiology. We have parsed, chunked, and encoded them into a retrievable, queryable RAG dataset. So we basically built an English interface to this. So when the scientist virologist in this case comes in with a question of sequence features or potential interactions, viral host protein-protein interaction discovery, whatever it might be their specific application, domain application, they can go and ask a question like talking to ChatGPT or Claude and have their answers based on 450,000 articles with direct attribution all the way to a link to the article on the corresponding ASM website. The technology to run this is currently built, and we have acquired a dedicated compute to support this, to serve this. Basically, we are in talks with the ASM right now to make this publicly available as a resource on the BVBRC website. During this Codeathon project, we installed and configured and ran the HiPerRAG. We received a few different types of queries from the domain experts. And this Codeathon really formed the foundation of future collaborations that will investigate, extracting sequence features, extracting new druggable targets, new pathogen host interactions. And it was a nice, productive introduction to working with domain experts who will be the users of this technology. This was all. Thank you.
Thanks, Ozan. So there is one question in the chat. Maybe you can answer it quickly. It says, PDF parsing can be tricky because PDFs are unstructured information readability. Has that step presented any problems in generating the embeddings?
Certainly, PDF parsing is indeed tricky, especially if you're working with journal articles that might date all the way back to 1972. These can often be in the form of scans, so they're not digital-born PDFs that have no associated metadata. So rule-based high-throughput parser is not going to be very accurate for these. For that, you need to use neural networks that approximate the process of OCR. And for that, we have NuGut, and we have PyMu-PDF, and we have built a meta strategy that will predict the quality of parsing when you use the cheap, fast parser. And if that predicted quality is below a certain threshold, that PDF is going to be escalated to the more costly, more accurate, GPU-accelerated neural network approach, which is Meta's NuGut. This work is called AdaParse, led by Carlos Sivenshu here, a fellow PhD student. AdaParse is the name, as an adapter parse, AdaParse. So that technology is allowing us to get accurate, high-throughput parsing.